Hi everyone, so today I'm going to go through and show you how to use other forms of acceleration to solve differential equations relating to acceleration, velocity and kinematics. So if we start by considering where these other formulas come from. So here at the start for acceleration, this is what's written on the formula sheet. And what you can see here are there are a few different forms for acceleration. The first one we already know. This is just saying acceleration. If we differentiate position twice, we get acceleration. So we're diffing our position twice with respect to t. That's how we get the first one. Our second option is that to get acceleration, we differentiate velocity, which we've talked about before. So diff velocity with respect to t. That's our second one. Then to get into the others, we can look at where these formulas come from. We know, we just established before, acceleration equals the derivative of velocity with respect to time. If we're then looking at the chain rule, we can break that up. We've got our dv and our dt, so we break it up into dv dt like this, and we can fill in the gap with dx's. dv dx is still there. We know that dx dt, the derivative of position with respect to time, is equal to velocity. So this is where we get our third expression or equation, for acceleration. To get the final one, we know we have this from just before. Now this second point is saying that velocity is equal to the derivative with respect to v of a half v squared. If I differentiate a half v squared with respect to v, I multiply by the power, subtract 1 from the power, I get v. So what this is saying is the derivative with respect to v of a half v squared is equal to v. So we've got that. Now if we substitute our second equation into our first one, we've got a dv dx, that was from here, and we replace v with our whole expression over here, d dv half v squared. Now using the chain rule again, that means that these two bits will essentially cancel out. Not quite, but we can think of it that way. And that tells us that acceleration is equal to the derivative with respect to x of a half v squared. And so that's our final formula that we can use. Now one of the tricks in this case, when it's in terms of x, we've got x and v together, that we want to use our fourth. Oh, it disappeared. Okay, so a equals 4x. If we're using d dx of a half v squared equals 4x, so what we can do now is we can take this d dx to the other side, because what I do is I say I'm going to integrate both sides with respect to x. Here on the left, that means integral of derivative cancels out and I'm left with a half v squared. On the right side, when I differentiate this with respect to x, I add 1 to the power, which is 2, divide by the power, so 4 divided by 2 is 2, and plus c. To find c, we need to substitute in our initial condition. So when x equals 0, v equals -3. So I'll get a half lots of -3 all squared equals 2 lots of 0 squared plus c. So that means that c will be equal to -3 squared is 9. c will be equal to 9 over 2. So that therefore tells me that a half v squared equals 2x squared plus 9 over 2. Now it asks us to find v in terms of x, so I'm finding v. I can multiply everything by 2. There we go. And now I need to take the square root. Now we've spoken about this before, but remembering that whenever we take the square root, we now need to think about whether we want the negative or positive version. If I tried putting my initial condition back in again, x equals 0, I'd get negative 3 equals plus or minus square root of 9. To make this correct, I need the negative square root. I know it doesn't happen very often that we end up with the negative one, but I need the negative square root, so that means v equals negative square root of 4x squared plus 9, which is our answer. Now, just quickly before we go on, I want to show you that if we were to use a different form of acceleration, we could possibly still get the same answer. So this time we're going to use our third acceleration formula, v dv dx, and this time we're going to use integration by parts when we integrate on each side, and we have done this before as well. So what I'm going to do is integrate with respect to v on the left and integrate with respect to x on the right. So that means this dx here can move over. When I integrate v, I add 1 to the power, divide by the power. Here, add 1 to the power, divide by the power plus c, and you can see we're getting exactly the same as what we had here. So sometimes it is possible to use both formulas or either formula. Okay, let's go on to our next part. So we now have a particle moves in a straight line when the particle's displacement from a fixed origin is x meters, its velocity is v meters per squared, its acceleration is a meters per squared, and we've been given that a equals 2v cubed. Now, it's in terms of v, which means we have to this time use v dv dx. We don't really have a choice this time. You could try something else, but it will become really difficult to integrate the way you need to. So we can divide both sides by v to give us 2v squared. Now, to be able to integrate, we will have to flip over our expression, which means we're going to get x is the integral of 1 over 2 v to the power of negative 2 dv. So to solve this, we add 1 to the power, which makes it negative 1, and divide by the power, which will make that negative, plus c. So x equals 1 over 2v plus c. If we now sub in, we can sub in our initial condition when x equals 2, when v equals 2, x equals 0. So 0 equals a quarter plus c, or c equals negative a quarter. So therefore, we get x equals 1 over 2v minus a quarter. The question this time says find the relationship between x and y, so it doesn't specify what form that relationship needs to take, so this is fine to leave it as it is. Our last example for today, this time we've got our acceleration here, but our main clue is this time it's in terms of v still, but we want to express v in terms of t. So because we know we're going to need t's in our answers, that means we need to set up a form for acceleration that involves t. So I can write this as dv dt equals 50 over 490 minus v. Now, like we always know, we think about, can we take this dt over to the other side? We can't, because that only has v's, so we flip both sides over. Oh, whoops, I kind of did that in one go, didn't I? Let's go back a minute. Okay, sorry everyone, let's see what I'm thinking. Try again. No, I don't want the rubber. Okay, here we go. This one is 490 minus v is currently in the numerator over 50. We flip it over, 50 over 490 minus v. So now when I anti-differentiate this, 50 is a common factor. It will be log base e of 490 minus v. Because the v is negative, I need to put a negative out the front and I add c. So if we put in our initial condition, it tells us the particle is dropped from rest. So that means when t equals 0, v equals 0. So we will get 0 equals negative 50 log e of 490 plus c, or c equals 50 log e of 490. So if we're putting all this together, t is going to be equal to negative 50 log e of 490 minus v plus 50 log e of 490. Now when we're adding these together, 50 is common, log e. Our positive term is log e of 490, so that will go in the numerator, and we're subtracting log e of 490 over v. So it will be 490 over 490 minus v. It asks us to express v in terms of t, so we need to rearrange. We can divide by 50 to start with. Then we can change it to an exponential equation. So e to the power of t on 50 equals 490 on 490 minus v. Do we need our absolute value signs? Let's try putting in a value. If I was to try t equals 0, on the left hand side I'd get e to the power of 0, which is 1. On the right hand side, if I put v equals 0, I'd get 490 over 490, which we also want to be 1. So we want the positive version of that, which means I can get e to the power of t on 50 multiplied by 490 minus v equals 490. I need to solve for v, so let's expand our brackets here. Okay, now we want to solve this. So I'm going to pop up here to the top. Where's my pencil gone? There it is. Let's come up here. So that means I can rewrite this as v e to the power of t on 50 equals 490 e to the power of t on 50 minus 490. If I divide everything by my exponential, it will cancel out of this first term. The second one, 490 divided by e, I can write that as a fraction, or I could write it as e to the power of negative t over 50, remembering that if I change it from the denominator to the numerator, the sign of the power will become negative. That is a perfectly fine answer. You might be asked to factorize on occasion, which means it would then look like this. And that's an even nicer answer, I suppose. Now, if you have any questions whatsoever, please don't hesitate to ask me. Otherwise, this is our last exercise on kinematics for you to get going on. Thanks for watching.